Welcome back to me recording the same fucking video again because I forgot to switch off my other monitor. Today we're going to be covering physical chemical properties. Well, again, I guess. And so let's quickly go and define a few terms. A physical property is a characteristic of a substance that describes how easily it will undergo physical change. A chemical property will do the same thing, except it'll describe how easily it undergoes chemical change. There are certain of these things that you're responsible for, and most of these properties can be understood in terms of the position of the relevant elements and the periodic table and chemical structures of these things involved. It'll serve to sort of review what you've covered so far in topic 4. Melting point, boiling point, and volatility. Let's quickly define those. Melting point is the temperature at which a substance melts. Boiling point is where it boils. And volatile describes how easily a substance evaporates. All of these properties can be they behave the same and for the exact same reasons. So we'll group them together as one, and you're expected to know the whys and explain the trends and use these to predict certain behaviors of different things. It's going to be a fairly long video, but we'll get to that later. The factors that affect the melting point, boiling point, and volatility. Firstly, we have the type of material. Obviously, the stronger the electrostatic forces within a material that hold it together, the higher the melting point is, and boiling point and volatility. The higher the melting point, the higher the boiling point, and the less volatile it is, since there are stronger forces of attraction holding each individual molecule together. So what this nets as a result is that network covalent compounds are the highest melting point and all that stuff, and followed by metals, followed by ionic compounds, followed by molecular substances. Um, for metals, this is pretty obvious. Um, for network covalent stuff, the melting point and boiling points and all that stuff, it's so high because covalent they're held together in a lattice type structure, which is already very organized. But the covalent bonds that are holding them together are much stronger than the ionic bonds holding ions together, since it's the electrons are evenly dispersed around the thing within the bond. So therefore, since they're evenly shared, the electrostatic forces between them are maximized. Whereas for ionic compounds, one thing clearly favors the electrons and the other one clearly doesn't, so it's easier to break those apart. For metals, it's quite simple. For metals, it's quite simple. Since they bond according to the electron C model, um, they their cations and anions are the things that are holding them together. Those are what cause the electrostatic forces of attraction, and therefore, since they are charges between full ions and they're full charges, they tend to be quite high as terms of melting points and all that stuff is concerned, since they're full charges. And then because they're cations, their ionic radii are much smaller. And now this will get me to an important point: is that as you go up the as you go up the groups, they tend to get higher in terms of melting point and boiling point and all that stuff, since the atomic and ionic radii are smaller. And as we know from Coulomb's law, um, electrostatic force is inversely proportional to the square of the distance, i.e., smaller distance equals stronger force. And then as you go across the period, since the radii is similar, we also note that higher charge ionic charges means stronger electrostatic force of attraction. Um, and then lastly, for molecular compounds, they tend to be weak, since the only thing that really holds them together as one cohesive unit are intermolecular forces. And that's what we're actually going to cover next. The type of intermolecular, for molecular substances, the type of intermolecular force plays a big role in determining the properties of these things. Um, Generally, since we know that hydrogen bonding is the strongest, that's obviously number one, followed by dipole-dipole forces, followed by induced dipole, induced dipole, and then lastly, induced dipole forces, because that's sort of the order of strength as they go. And the reason that is because, dipole-dipole forces, the molecules can line up their positive and negatively charged ends together, and have some sort of electrostatic attraction holding them together as one cohesive unit. And therefore, since it takes energy to break, they have higher since it takes more energies to break those stronger intermolecular forces, um, the higher the melting point and boiling point, and the less volatile they are. And then hydrogen bonding is much stronger than dipole-dipole forces in terms of magnitude, just because hydrogen is very small and can get very close to lone pairs of other atoms, can get very close to the negatively charged ends of other atoms, and in addition, they tend to be um, highly positively charged just due to the nature of what they're attached to. Um, Interestingly, here you'll note that when you come down here, you'll see the boiling points for the group 4, 5, 6, 7 hydrides. What's interesting to note is that, hey, these three all have hydrogen bonding, right? Um, why are they so drastically different? And the net result is just due to the fact that water has the perfect structure for hydrogen bonding. It can it can bond onto two other water molecules, and it can also accept hydrogen bonds from two other molecules. Whereas hydrogen fluoride, for example, it, it can accept three, but it can only give one. So it's a very uneven balanced sharing. And I suppose on this topic, because I get asked this question, quite often, I figured it's worth dwelling to spend some time on it as to why carboxylic acids have higher melting points than alcohols. So let me first quickly draw some molecules first, just so we can explain. Right, now that that's done, let's get into explaining why this is. So for this alcohol here, we can put this hydrogen, oops, we can put this hydrogen that can bond onto either this lone pair or this lone pair. Whereas with the carboxylic acid, we can focus on this hydrogen. It can go here, it can go here, it can go here, or it could go all the way over here. Since there's more spots for the carboxylic acid to accept hydrogen bonds, it'll pack more. It'll just have more of a packing effect than the alcohol, and therefore, since there's more packing, there are stronger. Although the intermolecular force strength is similar, if not the same, since there's just more of them, um, it has a higher boiling point since there's just more bonds to break as a whole, right? So hopefully that answers that. And let me quickly erase this stuff here. Select freeform. Eraser. This one, this one, this one. All right. Now that that's done, making sure I'm on the same screen, now we can look at the purity of a substance. Lastly, since there may be impurities in the substance, they might cause uncertainties in what their melting points or boiling points are, and therefore it'll melt or boil over a larger range of temperature. That's pretty obvious, right? The next physical property you're expected to determine is the solubility of stuff. Um, for network and metal substances, it's pretty simple. They don't dissolve. Metals may react to form water-soluble compounds, but the metals themselves will not dissolve in water. For molecular substances, the general rule is like dissolves like, i.e., polar things will dissolve in polar solvents, non-polar things will dissolve in non-polar solvents. However, you can't mix non-polar and polar together because that just won't work. The actual chemical reason for this is quite simple. The non-polar stuff will only interact with the non-polar stuff because it just does not interact, because although in practice it may interact with since everything has London dispersion forces, it would theoretically interact with the polar stuff. However, since the polar stuff has much stronger electrostatic forces of attractions with other polar things, in practice it will never really interact with them. So therefore, the nonpolar stuff tends to interact by itself, and the polar stuff interacts by itself. A useful analogy here that might help is sort of with foreign exchange students. Since there's a language barrier, the foreign exchange students will only tend to stick to themselves, and similarly, the white people will only tend to stick to themselves since there's no language barrier. Now, if you introduce some heat into it, if you introduce some heat into the system, then um, the solubility of nonpolar things in polar solvents will increase since there's more energy, and that means the electrons in the molecules will move around more, and there's more of a polarization difference, and you'll form essentially dipole-induced dipole forces. There's an energy barrier between that, and if we go back to our analogy here, it would be like giving the white kids a Chinese English dictionary to communicate. We can write solution reactions for the process of dissolving things in water, and for not for molecules, it's quite simple. It's just that. It couldn't really get any more simple than that, so I'm not going to explain more than that. For ionic compounds, however, things are a little bit more interesting. When you dissolve an ionic solid in water, what happens is that the water molecules will pull apart the ionic crystal. As you can see sort of here, you'll pull apart this crystal, and these positively charged ends of the water molecule will attract the anions, and then vice versa with the cations. The negatively charged ends of the water will go to the positive ions. Now, different salts have different solubilities in water. Generally, the higher the temperature, the more soluble they are in water. And they have something called the solubility constant, which indicates how much they dissolve in water. And when we go on to discuss equilibrium later on, you'll sort of get a sense as to why that is. However, you are expected to predict with some degree of accuracy the solubility of certain salts. Now, what does that translate to? This is an actual solubility chart. You're not expected to memorize this shit though, and I wouldn't. Just straight up. However, what I think is more reasonable to expect of you is to memorize this abbreviated form, where the most soluble and the least soluble. The most soluble cations are group 1 and ammonium, group 1 metals and ammonium, and the least soluble cations are cations of lead, silver, and mercury. For the anion side, the most soluble ones are nitrates and chlorates, and the least soluble ones tend to be hydroxides, carbonates, phosphates, and sulfates. And then for solution reactions, since we note that the crystal breaks up in water, we have to write out the dissociation or the separation of the ions, like so. And when you mix two or more aqueous solutions of ionic compounds together, you can have either two possibilities. All the ions will remain dissolved in water, and a precipitate will form if any cation-anion pair cannot form a compound that is soluble in water. You have to list out all the possible cation-anion pairs and find the one that is not soluble. Is quite literally what it amounts to. The easiest way to do that is to sort of build a cross. You can use a dotted line for something that's soluble, and a full line if it's not soluble. And the least soluble ions, the least soluble cation, the least soluble anion, will combine together to form an ionic salt. Will combine to form a precipitate. It's quite simple, really. Lastly, we're going to talk about electrical conductivity and the flow of charged particles. Electrical conductivity is defined as the flow of charged particles, and for something to be electrically conductive, it must have charged particles, and these charged particles must be able to be easily free to move around. Now, what things will conduct electricity? Well, things that we discussed have charged particles and these charged particles can move around easily. Metals are a very good example of a conductor, and we can explain this according to the electron C model. Since the electrons are delocalized according to the electron C model, i.e. they're free to move around across the entire metal block, they are obviously mobile, and electrons are charged particles, so therefore they are charged particles that can move. They should therefore be able to conduct electricity. Another example of a good conductor is an ionic salt. If you melt it, although in a solid state, it won't really conduct electricity because they can't move around freely. If you melt it, it'll conduct electricity, or if you dissolve it in water, it'll conduct electricity. For the molten salt, it's pretty obvious since it's melted, there's enough kinetic energy for the ions to move around freely, and since they have charges, ions are defined to be charged particles. They can carry a charge. However, in salt water, they can carry a charge by moving through the water. They can use the water as a medium to move across it. Uh, some covalent compounds that have delocalized electrons can conduct electricity, and that's what we're going to get to in the next video. Thank you for watching. Don't forget to like and subscribe.